In this video, we'll be talking about graphs of polynomial functions. We're just starting off though, so we'll first talk about transforming monomials. So up to this point, we've seen a few examples of polynomials. Most notably, we've seen linear functions, which have the form f of x equal ax plus b. Here, a is assumed to be positive because that has positive slope. Here we've also seen, here assuming a is positive so that this opens upward, we've seen quadratic equations, which are sort of second degree polynomial functions, right? This was first degree, so first degree, second degree, and third degree. And then we also have seen at least one example of a third degree polynomial equation, which is the cubic function. Okay, so we've seen a few examples here. These two we've looked at in detail. This one's still kind of a mystery, but hopefully through these next few videos it'll become a bit less of a mystery. Anywho, by using these functions as a template, we can notice two important things about all polynomial graphs. First off, they must be continuous, meaning they have no breaks, holes, or gaps. They also must be smooth, meaning they have rounded terms, not cusps or points. So what you notice here is all three of these graphs are smooth and continuous. They're continuous because you never have to lift off your pencil to draw them. And they're smooth because here there's no really sharp turns or points, right? So here you just kind of keep going and you never really turn. Here when you do turn, it's very gradual and smooth. And similarly here, it's also very smooth around 0. Let's look at a few more examples though. For instance, this example would be continuous and smooth. This example, however, would not be continuous. And if it's not continuous, we automatically say it's not smooth as well. So that also tells us that it's not smooth. Okay. Here, however, we have something that this is both smooth and continuous again. So it is continuous, no breaks. And this is smooth as well. So here we also have that this one is definitely continuous, but not smooth. And why is it not smooth? Well, it's not smooth for a couple of spots. Here, there's too much. This is what's called a cusp. And basically what happens is you get sort of a point there, and that creates non-smoothness. And then here you also have a point. So this causes, it's too sharp of a term and it's not rounded, and so it's not actually smooth. Here, it's not continuous over here because of, well, that jump, that break in the graph. Moving on, we can also notice from our experience with quadratics that if we have a transform power function, that is a function of the form f of x equals x to the n, where n is equal to 1, 2, 3, 4, 5, etc., then we can always graph it provided we know what f of x equal x to the n looks like. Something to be warned about, and I'll talk a little bit about this afterward at the end of the video. In general, though, we cannot just complete the cube or the fourth or whatever, okay, for degree 3 and above. So, in other words, if you're sort of hoping that this can be just like graphing quadratics, you're going to be disappointed. So let's jump into this. Let's ask ourselves, what does x to the n look like? So let's start with these first 4 we actually know, and then using those we'll go ahead and look at what happens here. So I want to go ahead and do these in detail. So for the first one, it looks like just the function 1, right? Because anything to the 0 power is just 1. So in other words, what happens here is, basically y always gives you the value 1 back, okay? What about for x to the first? Well, it's also easy to graph, as we've seen multiple times, because this is really just equal to x, right? And that's a line of slope 1 and y-intercept 0, so it looks just like that. course, you could also see that plugging in 1 gives you 1, plugging in -1 gives you -1. This is just the identity function. We've also seen what y equals x squared looks like. So we know it's just the parabola that opens upward, but that can be a little bit misleading for where we're going to be going in a bit. And namely, here if we're a little bit more careful, we'll see that 1, of course, plugging in 1 gives me 1. But if you plug in 1/2, you actually get 1/4 here. If you plug in 1/4, you actually get 1/16. If you plug in 3/4, you get 9/16. And of course, we know that this function is symmetric about the y-axis. And so, because of that, this side will look the same as this side. Well, and then let's go ahead and look at x cubed. So looking at x cubed in detail gives us that here we see that 1/2 will, cubed becomes 1/8. So this is really far down. And so what we see is happening is it's sort of gradually, as we increase the power, it gets the graph is getting pulled closer and closer to the x-axis, okay? We'll see something similar happen with x to the 4th and x to the 5th. Namely, x to the 4th looks just like x squared, except what's happening is the parabola is slowly getting sort of leveled out down here. And again, because it's an even power, it's still going to have that y-axis symmetry, okay? Of course, then you expect x to the 5th to look a lot like x cubed, except again, more flattened out. Namely, so again, here we do see that it actually starts to flatten out as time goes on. Okay, I picked a few extra values here, namely, you can use the fact that you know that where 1/2 and 3/4 go. You can always use a calculator if you want to kind of get a few decimals here. But again, this is roughly what happens. And I mean, a graphing utility like Desmos will show you this much easier as well. But again, notice here, all of these are continuous and they are all smooth. So again, I didn't just sort of connect the dots with lines. I know that they have to be smooth. Okay. Of course, knowing once you have new parent functions, you then can go ahead and sketch translations of them. So let's go through and sketch a graph of each of these functions. Well, here, again, we know x to the 5th will look almost like the cubic function, except sort of pulled down more. But then we go ahead and this gives us a reflection in the y-axis, right? So this is a reflection in the, sorry, did I say y-axis? I meant in the x-axis. It's a vertical reflection. Okay? Well, then that means that what was here will get sent down to here. What was here will get sent up to here. 0 will stay put. And then we got to figure out the rest of the points. Well, I like to map 1/2 to kind of give me my graph structure. So the halves, where does that go? Well, 1/2 to the 5th is 1/32, so that's 1/2, 1/2, 1/4, 1/4, 1/8, 1/8, 1/16, 1/16, 1/32, 1/32. So way down, sorry, it's negative. So way down here. Okay. And then you draw a nice smooth graph between them, right? There you go. That's f of x equal x to the 5th. Okay, something like that. X plus 1 to the 4th will look just like x to the 4th, except that now we're going to shift it left by 1. Namely, what was here will get sent over here. The vertex for our flattened parabola will get sent to there. What was at 1 will get sent over here. Same with what was here will get sent over here. And then again, we need to ask ourselves sort of what happens in between. Well, 1/2 to the 1/2 to the 4th is what? 1/2 to the 4th is 1/16, so that's 1/2, 1/8, no, 1/2, 1/4, 1/8, 1/16. So that would go there, that would go there. And then we get, you could always make this a little bit better by using, I don't like that, it's too, it looks too pointy. There we go. There we go, something like that. There we go, like that. This side's a little bit better than this side, but oh well. There we go. Alright, and now it's time for you to try an example, so go ahead and sketch the graph of each of the following functions. On the count of 3, I'll reveal the solutions. 1, 2, 3. So these graphs actually help you see just how bulky this x to the 4th truly is. Here we just shifted over by 5 to the left. That's not too bad. Here, but the rest of these graphs are enlightening. These two are very similar in that this one is just the negative of this one, so you expect it to be a reflection, right? But here what we did is we had x to the 4th minus 7. That means we shifted all of x to the 4th down by 7. To get some real scope though, you can see that this thing, it doesn't just the parabola doesn't just get flattened down here, it also sort of gets expanded out the other way. So the whole thing kind of gets ripped apart as you add the power there. Similarly, so again here, this is just a reflection because this is the same thing as negative x to the 4th minus 7. So it's really just the flip of that. This one's interesting because this shows you that here, if I was to put 4 out here, I would see that since 4 to the 4th is 64, if I divide by 4, I would get, actually that's not even high enough, is it? No, 2 to the 4th, sorry. 2 to the 4th is 16, so if I divide by 4, I'd get 4. So that goes out to there when I go 2 away. But over here, everything else gets flattened a lot, right? Down to 1 gets sent down to 1/4. And so I'm further sort of flattening out the parabola. This is not the whole story, and so for instance, a question you can ask yourself is which of the following functions is x to the 4th plus 2x cubed? The big issue here is you can't really write that as a transformation, right? So then, instead, what you kind of need to do is you can say, well, we know the zeros, right? So the zeros, we know x to the 4th, we can factor that as x cubed comes out times x plus 2. So we should have a 0 at x equals 0 and x equal negative 2. Well, we'll see here that this does not have a 0 at 0, so that doesn't work. This one does have a 0 at 0, and this one does have a 0 at x equal 2. This one has a 0, 0, but not at x equal 2, so this doesn't work, so this must be our graph. Okay? So you can use a bit about that, but of course, this is only a little bit, right? You're looking at the zeros. A better question is, are there any other properties to help with graphing? Well, that's what we'll be looking at in the remainder of the videos for this section. If you would like some more practice, be sure to see the textbook and work problems number 1 and 9 through 18. In our next video, we'll talk a bit more about how we can improve our understanding of graphing polynomial functions by looking at the leading coefficient.